Good morning, everybody, and welcome to the second day of CoRL. It's my great pleasure this morning to introduce our second keynote speaker, who is Dorsa Sadigh from Stanford. So Dorsa works in human-robot interaction. She's somebody who thinks deeply about models of systems, and she comes from a background where she's been interested in formal verification of systems. So she approaches this problem of human-robot interaction from a background of thinking about probabilistic modeling and verification, where she's made some deep contributions to linear temporal logic specification, in particular probabilistic signal temporal logic and chance-constrained temporal logic. So she, from the very beginning, when she started working on these research problems, she was interested in human behavior. She worked in human interface design, working on projects in human driver behavior. And then these kind of directions came together as she started thinking about models for how humans interact with robotic systems, and then how one might design robotic systems to work well with the people they have to work with. As she's developed her lab at Stanford, she's got a number of exciting projects in robotics, both autonomous cars and personal robotics that work, for example, in co-manipulation tasks, where she and her students are working on projects related to information gathering over human internal state and preference-based learning of reward functions. So Dorsa got her PhD at Berkeley, and since September 2017, she's been an assistant professor in computer science and electrical engineering at Stanford. She's won a number of awards, including the AFOSR Young Investigator Award, the NSF Career Award, research awards from Google and Amazon, and a large number of Best Paper Awards and Best Paper finalists. So, for example, she is one of the finalists. You heard the announcement yesterday morning. She's one of the senior authors in the Best Paper Award finalist for this conference, which you'll hear that paper a little bit later this morning. Also an award finalist for RSS, HRI, all this year and last year. So congratulations, Dorsa. So it's a great pleasure to introduce Dorsa, and Dorsa, take it away.
Thank you so much. Thanks for the kind introduction, Claire. And yeah, thanks for inviting me. Really excited to be here. So let me start sharing my screen. Everyone can see it? Is up? Yes. Okay. All right, so let's get started. So yeah, I'm Dorsa, and I work on algorithmic human-robot interaction. And today what I'd like to do is, I'd like to walk this boundary of robot learning and human-robot interaction to try to understand what robot learning can do for human-robot interaction, and also like what can we learn from interactive autonomy for robot learning in general. So what is that boundary? How can we do that better? So if you think about the field of robotics, over the past decade, we have seen a lot of advances in this field, and we have finally got to a point where we can think about intricate and long-term human-robot interactions, right? Like we see this in autonomous driving, as autonomous cars are interacting with human-driven cars or pedestrians, and we are starting to see this as robots are entering our homes, like when we have service robots or where we have assistive robots trying to help us feed ourselves. But still, there are quite a bit of challenges here. And I think one of the big challenges here is thinking about that interaction between the robot and the human and trying to make that as effective and as seamless as possible, just like how humans do it. So if you think about human-human interaction, humans are amazing at this. They easily come to each other's spaces, and they collaborate and coordinate with each other on complex manipulation tasks. And a good question to ask is, well, how is it that humans are able to do this? How should we model even human-human interaction? So let's think about that for a few seconds. So imagine that we have two humans that are coming together, trying to do a task together, a collaborative task, or maybe a competitive task. Let's say these two people are trying to play a game of chess. So one way of modeling this interaction is to assume that each one of these agents is going to have some model, some representation of the other agent. Basically, it's going to have some model of how this other agent is going to play on this game of chess. And we can even go further and think about the fact that this opponent is going to think about us thinking about them. And we can kind of like have this infinite regress of recursive reasoning of me thinking about you, thinking about me, thinking about you, right? And that's often referred to as theory of mind in human-robot interaction or in robotics in general. So this idea is not also common to robotics. This shows up in a variety of fields, right? In reinforcement learning, this is called opponent modeling. In natural language processing, this is often referred to as pragmatics and rational speech act. And in general, in all of these fields, like people have realized that if you want to do full-on theory of mind and full-on game theoretic modeling, it turns out to be particularly expensive, this type of recursive belief reasoning. So what ends up happening is that people have approximations of this. Instead of doing the full game, maybe they cut it at the nth time step and they do nth order theory of mind. So this is also common in human-robot interaction, right? Like maybe doing first-order theory of mind, where we assume that there's a human and the human has a model of the robot. And at the same time, maybe the robot has some sort of model of the human and they come together and we think about coordination based on that. This is an idea that we have actually used in an autonomous driving setting. So in an older project, we looked at how we can plan for an autonomous car based on this type of game theoretic reasoning, based on having models of the human. And we were able to, like thinking about this full system of human and robot interacting with each other, we were able to get very interesting behaviors. For example, we were able to get behaviors where an autonomous car kind of acts like this white car here, and it starts nudging in front of other drivers and kind of like make them slow down, make them respond, which is pretty interesting. It's a very interesting interaction that you would get here that you wouldn't normally get if you weren't thinking about this type of interactive behavior. And I want to emphasize, this is beyond coordination. This is not just coordination between the two cars. What ends up happening is that the white car here is influencing the other agent and making the other agent slow down, right? Making that other agent to not go 60 miles per hour anymore, which is a pretty interesting point. And the reason I'm emphasizing it is I'm going to come back to this idea of influencing later on in the talk. But going back to our theory of mind story, I think this idea, this perspective kind of works out nicely in a variety of human-robot interaction settings. But the thing I would like to argue is that a lot of interactive tasks are also not like playing chess. Actually, a lot of interactive tasks are kind of like this. Like you have two people coming together, like Alex and Bob coming together, trying to build an object together. In this setting, I really don't think Alex is thinking, well, I wonder what Bob's belief of the world is or what Bob's belief over my policies are. Like, I think something simpler is happening here. Like, one thing I know about humans is that they're bounded rational and they're not going to be able to capture these high dimensional beliefs, right? So I think what is happening here is people are keeping track of a much lower dimensional representation that is almost sufficient for doing the task. That's a shared representation based on the task and is enough for achieving the task. And humans are really good at picking up what that is. And you even often have names for it, right? Like we call it roles, like who is leading, who is following, or we call it intent or goal. And you might be asking, well, what is the big deal here, right? Like people have done belief modeling over goals and intents like over the years. Like, why am I making a big deal out of this? Well, this is actually different. Like what I'm proposing here is not necessarily having a set of intents and trying to do belief modeling on that. What I'm proposing here is trying to figure out what that shared representation even is, right? Like without having any prior knowledge of that. And how is it that humans are able to figure that out like fairly quickly? So going back to this idea, like this is a core idea that I'm gonna come back to throughout the talk in general. This idea that in general, when we have interactive tasks, there is this orthogonal perspective to theory of mind, which basically says, well, don't worry about modeling everything about the other agent. Maybe there exists some low dimensional shared representation that can capture the interaction here and that you can use for coordination and collaboration. And even you can maybe go further and use that for adaptation, the fact that that person changes over time. Maybe you can capture that, the fact that that person changes and the non-stationarity of the other agent using this low dimensional representation. And mathematically, this low dimensional representation is fairly similar to some notions of sufficient statistics, right? Like what are the things that are needed for achieving this task together? So having that in our mind, right, like going back to this example of two agents coordinating, I think there are a few points that are kind of important here. One is the fact that, well, there is this person, Alex or Bob here, and both of them are changing and they're non-stationary, right? Like they're learning, they're getting better at the task. And we can't assume that they have some sort of fixed reward function or policy, right? Non-stationarity is actually a challenge here when you're actually thinking about coordinating with people. The other point that I think is important is if I'm trying to build a robot that coordinates with Alex in the same way that Bob is coordinating with Alex, I should be thinking about how that robot can coordinate, collaborate, and further maybe influence, kind of like the car example I was mentioning earlier, right? Like in this case, the white car was influencing the other driver to make this coordination happen. And it was for this better good of like doing this marriage maneuver. But maybe the robot has some sort of objective, and based on that, it could influence and coordinate. And then furthermore, I think this latent representation, this idea of figuring out what is that core that we need to capture from the interaction and use that for better coordination is kind of useful and important view for achieving this task. It's a perspective on trying to do better coordination. So with that, my plan today is to talk about three main topics, three vignettes that try to capture some or all of these ideas of non-stationarity, coordination or influencing, and this idea of using latent representations. So I'm going to start talking about learning latent intent or latent strategies during coordination. Then I'm going to switch topics and think about it from the perspective of learning from interactions, learning from humans, and talk about learning reward functions. And for the last section, I'm going to talk about learning latent actions for better coordination. All right, so let's just get into it. So going back to this example, I really think when we are interacting with other agents or humans are often non-stationary, and they tend to update their behavior in response to the robot. And ideally, we would want to be able to capture that. Let me give you an example here. So imagine we have two robots coming together. We have an ego agent, which is on the left. This is the robot that we are trying to plan for. This is our robot. It's a learning agent. And then on the right, I have this other agent, which is this other robot. And this other robot is following some rule-based policy, like going to the left, pushing the puck to the left, or pushing the puck to the right, or pushing it to the center. And yeah, you're playing game of air hockey here. So imagine that these two robots are trying to play this game of air hockey together. So then an interaction is going to be a sequence of state and actions and rewards from the perspective of the ego agent. If the ego agent is getting a reward or not comes into this interaction. And then if you think about this other agent, if it pushes the puck to the left and let's say the ego agent blocks it, it's going to change its policy and then push the puck maybe to the center because it might think that the ego agent is good at blocking on the left. And then it follows some sort of dynamics. And that dynamics is this F dynamics, which is based on the previous value of its state, which is Z, and also the interaction that it sees. And the idea is that the ego agent here doesn't really have access to this F. It doesn't know how this other agent is changing its strategy. The only thing it observes is just that interaction and the reward that it gets. So the question that I think is interesting here is how can we model the other agent? And the way we go about it here is by collecting these past interaction and trying to encode that to a low-dimensional representation, a latent strategy. We call this a latent strategy that is able to predict the next interaction. So the way we are training this latent strategy is using this autoencoder based on the past interaction. We are trying to capture the core that is able to help us predict the next interaction. And this basically captures, like in a sufficient manner, how the other agent is changing and responding to our actions. So now that we have this latent representation, now that we have this latent strategy, what we can do is we can basically plan for our ego agent. We can do reinforcement learning for our ego agent. And the way we do that is by maximizing the expected return of the ego agent. But this reward function now is going to be conditioned on the latent strategy, on the fact that this other agent is changing, and then now we know what that representation looks like. So if we maximize this expected return within an interaction, what ends up happening is that we end up being able to get a policy for our ego agent, being able to react and collaborate and coordinate better with the other agent. And this is actually a CoRL work, and Annie will be talking about this immediately after this talk. And we call this algorithm Lily, learning and influencing latent intent. So let's see how Lily works. So let's go back to this air hockey example. So if the ego agent blocks the puck, we are getting reward of +1. We're saying, well, the ego agent is going to get a reward of +1. And we are designing this experiment. So if the ego agent is blocking the puck, particularly on the left, then the ego agent is going to get a reward of +2. Maybe it is easier for the ego agent to block it on the left. So you're designing it so you get higher reward if you go on the left and block it on the left. Okay. So if you use state-of-the-art reinforcement learning, like soft actor critic, what ends up happening is after starting with an initial policy and then training it for, let's say, 2 hours, our ego agent is able to learn a policy that blocks the puck only in one mode. So for example, in this case, it learns to go to the right, and that's the only thing it learns. Because again, it doesn't model anything about the other agent, so it just like gets good at one of these modes. And at some point, it might realize that, well, actually going to the left is better because I'm gonna get a higher reward there. I get a reward of +2. So finally, after 4 hours of training, it's gonna realize that, and it's just gonna go to the left and always go to the left. And by always going to the left, basically soft actor critic is able to block the puck like 40% of the times. So this is actually a plot of success, not reward. So what ends up happening is soft actor critic starts blocking it on the right, and at some point it switches and always blocks the puck on the left, getting like 40% success. Okay? So what happens if you use Lily? So if you use Lily after 4 hours of training, our robot is able to block the puck no matter where you push it, because it does model this latent strategy. It captures how the other agent is changing. And in terms of success rate, we are going to be around 90%. So 90% of the times we are blocking the puck because we are capturing how the other agent is changing and how we should coordinate with the other agent using this representation. Okay, so that's all great, but we could even do better here. So going back to this formulation, right? Like this allows us to react to the other agent. But what if you want to influence the other agent, right? Like I know blocking the puck on the left is better for me. That's going to give me a reward of +2. Can I influence the other agent to get the puck always on the left? So the way we do that is actually, instead of maximizing the expected return within an interaction, we maximize it across interactions. So we consider a more global view. So the ego agent, from a global perspective, maximizes the expected return over all these interactions, and that allows us to actually influence the other agent. So using this type of policy, Lily with influencing, in terms of success rate, we are actually doing fairly similar to Lily. Like we are going to get like 90% success rate. So if you push the block any direction, it is going to block it. And this is actually the success rate plot, so it kind of like looks similar. But the thing that is different is using Lily with influencing, we are actually going to be able to get the puck on the left more often than normal, right? So we would be able to influence the other agent to push the puck to the left like 41% of the times, as opposed to like uniformly getting left, middle, and right, where we get in the no influence scenario. All right, so what is the key takeaway here? So I've been basically talking about the fact that human partners or other agents, other partners that you're coordinating with, they're often non-stationary. And then we should try to capture that non-stationarity. And one way of doing that is by capturing that using a low-dimensional latent strategy. And what Lily does is it anticipates this partner's behavior using latent strategies in order to react and influence to the other agent, which is kind of nice. But the thing I want to emphasize here is, at the end of the day, I'm very interested in getting these robots coordinating with people, right? Like actually having a person in the loop. And we actually tested Lily with humans in the loop, and we had some promising results. But when it comes to training with humans, it's incredibly difficult to bring in the human in this training loop, right? Like train this reinforcement learning with data where we are collecting from actual humans. And if you don't do that, like that makes our policy fairly brittle when you're interacting with actual humans. So the thing that is difficult is that if I want to bring in humans and interactions with humans and try to help robot learning based on interactions that I'm getting from humans, that ends up being fairly expensive and impractical at times. So going back to this diagram and what I've been talking about, basically I've been talking about this idea that there are evolving interactions and there are non-stationarities. And we could capture that in an efficient manner using latent strategies, and that's pretty nice. With that, you're able to capture non-stationarities, we can coordinate and influence, and we are using latent representations. But the thing that we don't actually get is this idea of getting data from humans and being able to train this reinforcement learning agent with data that is directly coming from humans. And I think it would be useful to be able to learn something from interactions with humans and try to merge that a little bit more. So in the second part of the talk, what I'd like to do is I'd like to just focus on that. I would like to think about how we can learn from interactions with humans and why that is useful or why that is feasible in settings. And for that, I'm going to simplify everything else. So for the second part, I'm not going to worry about non-stationarity. I'm not even going to worry about what the robot does, like if it coordinates or influences. I'm not even using my latent representation. What I'm going to focus on is just trying to learn from humans and see where we can get from there. And the idea that we are looking at here is, can we learn reward functions, human preference reward functions, so a robot can do the task the way that the human wants it? How can we bring in human data there and efficiently do that? And our key insight here is really the fact that most prior work that tries to learn from humans, like, usually assumes that we have access to some sort of experts' data, and that is like the only way to go about it. But I'd like to argue that humans are kind of like leaky pipes. They leak information like from all sorts of different sources. It's not just expert demonstrations. And looking at just expert demonstrations is only like one source, and it doesn't allow us to think about all these different types of avenues and sources and streams of data that are coming from humans. So what do I mean by that? Imagine we have a robot that, let's say, wants to pick up an object. And one way of doing that is by basically collecting expert demonstrations from a person, and based on those expert demonstrations, go ahead and pick up the object, right? Like, that is one way of doing that. That's called imitation learning. It's a very popular area. We saw CoRL papers going up in that area this year. It's been around for 20 years. And basically, the common paradigm there is, let's collect a bunch of expert demonstrations. Let's learn a policy or a reward function that captures and imitates expert demonstrations as closely as possible. But you're not really limited to just that, right? There is quite a bit of number of suboptimal demonstrations and observations out there. There are YouTube videos of people like cooking. And if I could use that, if I could actually use that, that would be wonderful. Or, for example, there are other sources of data, other modalities of data. For example, like, there's language instructions and narrations that has a lot of information in it. And if you could use that along with some of these other types of data, that would be awesome. Or other types of data are things along the lines of pairwise comparisons and rankings, right? Like, if you think about demonstrations, providing demonstrations on these robots with high degrees of freedom is usually pretty challenging. But if you can get the robot show you a bunch of trajectories and just ask you, well, which one do you prefer, or what ranking are you giving? Like, from that, I should be able to better learn like what the reward function is in a more practical manner. And finally, I want to emphasize that this robot is an embodied agent, right? It's different than an AI agent. It's different than just like usual ML, right? I can actually move this object. And given that I can actually move this object and provide physical corrections on this object, could I learn from those physical corrections? So these are areas that, in general, my group is pretty interested in, and we're doing work in all of them. But today, what I would want to do is I would want to just focus on two categories of things. So thinking about learning from pairwise comparisons and how we can do that actively and efficiently. And then I want to briefly talk about some of our recent work around learning physical corrections at the end. Okay, let's get into it. So what do I mean by pairwise comparisons? So what I mean by that is I can show two different trajectories to a user. I can show A and B, and then ask a user, well, which one do you prefer? And based on the human response to this binary question, I'm going to get some information about the underlying reward function that exists here. And for the moment, let's assume that this reward function is a linear combination of a set of features. So let's assume that there are some set of hand-coded features coming by a designer, and then this reward function is just some theta parameters. These thetas are weights for each one of these features, like, added up together. And the thing I'm trying to learn here are really the thetas. These are the weights, the parameters of my reward function. So imagine theta lies in a three-dimensional space. Then every question, every query that I'm asking from the user generates a separating hyperplane in this space. And then the human's response is going to basically tell us which side of the hyperplane is preferred. And based on that binary question, I'm going to get a better estimate of where the true theta through parameters really lie in this space. So then that's one question. But then the interesting research question here is, what is the sequence of most informative, diverse questions that I can ask a user in order to better learn what the reward function is in an effective and efficient manner? And we formulate this problem as an active learning problem. So our goal here is to actively synthesize queries and questions where we query the person and learn the reward function. So what does that mean? What that means is I'm going to come up with scenarios, fees here, fees correspond to those scenarios, separating hyperplanes, that try to maximize the information that I would receive from that particular query. And the objective here could actually be any information theoretic metric. We have tried entropy, we have tried determinantal point processes. In this case, I'm showing volume removal. So this is basically the volume that would be removed from the hypothesis space based on that question that you're asking. And that basically captures the fact that you are trying to optimize for asking a question that's the most informative thing in the world right now in my hypothesis space. And then we also have a set of other constraints here. We want to make sure that these queries that you're generating satisfy things like dynamics. So that is what the constraint is adding. So it makes sure that the scenarios are actually feasible and can run on the robot. And in addition to all of these, we assume that humans are also noisy to some level. So we incorporate a noise model of the human. So we don't fully trust the person if the person tells me I like A over B. But once we have this formulation, the idea is that every time step, I can run this optimization. Based on running this optimization, I can generate my next query, get the answer, and then go from there. And what that gets me is an effective and efficient way of learning reward functions. I'm showing this in a simple scenario here. So this is a simple 2D driving simulator where we have this autonomous car, which is the orange car. And after 0 queries where it doesn't really know what to do, after 30 queries, the car learns how to keep heading. And then finally, after 70 queries, the car learns how to keep heading and do collision avoidance and so on, which is kind of nice because, again, there was no expert demonstrations here. This is just based on 70 simple binary questions. And from 70 simple binary questions, we were able to learn like how to drive in this simple simulator. And that kind of shows the power of all these other sources of data that I really think we should tap into. So going back to this picture, I've been basically talking about the fact that, well, there's this underlying reward function. Let's try to capture what that is. And so far, I've been assuming this reward function is a linear combination of a set of features. And then that's pretty difficult, and that's not always the case, right? If you consider a robotics case, a lot of robotics cases are not like of the form of a reward, don't have reward functions of the form of a linear combination of a set of features. Let me show you an example here. So imagine that we have a robot that wants to play a version of mini golf. So this robot wants to push this ball here to any of these targets down the table. And it wants to do that through preference-based learning. So what it wants to do is it wants to show us trajectories, like 2 different trajectories, and then ask a human user, well, which one do you prefer? And based on that sequence of queries, it wants to figure out what the reward function should be. So if I assume my reward function is a linear combination of set of features, I should figure out what those features are. And writing out features in general is pretty difficult. If you look at other robotics papers that try to do the same thing, they usually have like text like this in their papers. They have, well, let's pick a feature that is an exponential of minus C4 times D4. And I'm going to pick C4 to be equal to 3. You might be wondering, well, where does 3 come from? Or like, is that like magic? Like, where does this number come from? Or you might have more complicated features like exponential of some distance in D2 and D3. And then we'll pick C2 to be 7 and C3 to be 3. Okay. So these numbers are not magic. They're coming from a lot of hyperparameter tuning. And basically that tells us that coming up with features can be incredibly difficult for some of these tasks. So what can we do? Can we do better? You might say, well, this is an old problem, right? Like feature generation is a thing that we could do. We could come up, like we could use deep learning, right? That's the whole point of using deep learning, so we don't write out these features. But the thing is, the moment you go there, then bringing the humans in the loop is also going to be really challenging, right? So if you use just classical like deep learning methods, then you should like think a lot harder to think about how you can learn from humans and how you can learn from these interactions with the humans. I want to mention one other point here. So if I don't want to worry about that feature design, and if I just want to pick like the simplest features in the world, like shot speed and shot angle, One other issue that could come up here is that I'm not even able to capture everything with a linear reward. If I use a linear reward, that linear reward with these simple features is always going to just capture the corners, and I'm not going to be able to get any of these other targets, because maximizing this reward always get these types of corners and boundaries, and not any of these other targets. So ideally, what I would want to do is I would want to use simple features, these here, and then be able to have a nonlinear function on top of them that allows me to pick any of these targets that are as main target, any of these targets as possible targets. And the way we do that is by using Gaussian processes, actually. So what we do is we do active preference-based learning over Gaussian processes, and using these simple features that actually allows me to target any of these goals down the line. I'm skipping the math detail here. This is an RSS paper. If you're interested in reading more about it, you can take a look at the details. And it's not easy to do active preference-based learning over Gaussian processes. So there are some math details that goes in it. But let me just show you how this works in practice. So if you look at the learned policies, if you use that linear reward, it's always going to target the boundaries. We're not able to even learn this task based on linear reward. But if you use a Gaussian process reward and do active preference-based learning over Gaussian processes, we are going to be able to target any of these goals based on the human preferences, which is kind of nice. All right, so let me go back to this diagram, right? I've been talking about pairwise comparisons and the fact that we can learn from that. And now I want to basically talk about physical corrections as another source of data, as another useful source of data in order to learn reward functions. So it turns out that if you have robots and they have bodies, you can actually move them around, and the robot can try to learn from that. And the thing is, if you have a robot that is trying to help you, let's say, unpack groceries, the human can provide a sequence of corrections on top of it. It's usually pretty difficult to correct the robot with one single correction. And that sequence of corrections are usually interdependent, and they kind of build on top of each other. And an idea that we have been thinking about here is, could we learn from a sequence of physical corrections by actually considering the interdependencies between these different corrections? Let me explain this over an example. So again, imagine that you have this robot that wants to unpack groceries, and the two robots are helping you here, and they're trying to put the bag on the blue region. That's where the robot thinks the bag should go. And there's this human, and the human has different preferences here. The human really wants the robot to put the bag on the green region. Maybe the human knows something that the robot doesn't know. Maybe the blue region is red. Also, the human has a bunch of other objectives here. It doesn't want to stretch the bag too much because that breaks the bag. At the same time, it doesn't want to squeeze it too much because there's food in it. And it doesn't want to hit the obstacles like the Stanford hat or cabinets around, and so on. And the idea is that the robot is going to start off following this black trajectory, thinking that, well, I can go and place this bag on the blue region. That's where I'm going. And then the idea is that if you have a human here with these two robots, each one of them 7 degrees of freedom, the human is not going to be able to correct everything and satisfy all the priorities at the same time. Instead, the human is going to give these corrections by pushing the robot and a sequence of them to get the robot to do the same thing. And based on each one of these corrections, you're going to get a propagated trajectory based on the robot's belief of what the reward function is. And it can update that belief in an online fashion based on that sequence of queries that it is getting. And again, I want to emphasize that each one of these corrections, one at a time, is not going to capture everything. Even the last trajectory was hitting the Stanford hat. And then it's the sequence together that captures all the information about the reward function of the human. So how are we doing this? So the way we do this is, at the end of the day, I want to have a better estimate of theta, which is the parameters of my reward function. And if I think about probability of theta given corrections, well, I can write out Bayes' rule, and I have this posterior, which is probability of the corrections given theta. And these corrections are interdependent. So let's say I have k corrections, so psi1 through psi k. And the question is, how can I find this posterior? So here we are making this assumption that probability of these corrections that are given by the human, the sequence of corrections that are given by humans, is proportional to exponential of some sort of objective, some sort of reward function, which is a common assumption made when we are thinking about how humans act and give us corrections in this world. And the question is, well, what is that d? The way we are formulating that d is to have this trade-off between reward of each one of these trajectories discounted over time, as well as the human effort, right? Like the human doesn't want to push too much or provide too much force here. So that combination together is creating this objective, this D function. And at the end of the day, that helps us figure out what this posterior is. Computing this posterior is not particularly easy. Like again, like computing the partition function here is going to give us a lot of troubles because of these dependencies between the trajectories. And we're making a set of approximations, like Laplace approximations and mixed integer programming to make this actually work. But at the end of the day, we have the posterior and we can have a better estimate of theta. Okay, so let me show this in practice. So here I have this person basically teleoperating, basically moving the robot arm and providing this feedback. And I'm comparing my algorithm, which learns from the sequence models, with an independent baseline where we're independently thinking about each one of these corrections. And here the darker colors correspond to the true preferences. And using our algorithm, we have a higher belief of the true preferences as opposed to this independent baseline. All right, so I've been basically talking about this idea of learning from humans and trying to bring humans in the learning loop. And the reason that I think that is useful is, and there's a way of doing that, is that humans leak information everywhere. Maybe we should try to use that information, all sorts of data that you're getting from humans, in order to better learn what they want and actually bring them to the robot learning loop. So now that we have that, for this last part, what I'd like to talk about is this idea of still learning from humans, but bring this similar ideas of latent representations to help us coordinate better and have the robot do the task in a more efficient way. And for that, I'm going to focus on a specific application. I'm going to focus on the application of assistive teleoperation. So if you think about these wheelchairs with robot arms on top of them, there are actually more than 1 million American users actually use them for various types of assistive tasks, like getting out of the bed or feeding themselves. And it's incredibly difficult to use them. So here is this person using a Jayco arm to try to do various types of tasks in homes. And here the person is basically using the joystick and controlling 6 things at a time, like X, Y, Z, and yaw pitch rule of the end effector. And that makes it really unintuitive and difficult to use, and you have to do all these mode switching type things to do anything at home. So an idea that we've been thinking about is that, well, if you think about these assistive robots, they're dexterous, sure, this dexterity makes them useful, but it also makes them hard to control. So the question is, can we find a low-dimensional representation here that makes controlling these robots more intuitive and easier? And you might be asking, well, Dorsa, why do you think such a thing even exists, right? It doesn't necessarily exist if you want to go from any point in the state space to any other point in the state space, right? Like for that, you do need all those degrees of freedom. There's a reason they exist. But the thing is, conditioned on a task, if you know you're doing a specific task, conditioned on the context, you might be able to learn a low-dimensional representation. So let me give you an example. Imagine I have a high-dimensional robot arm, and I know this robot arm is moving on a sine wave. One way of controlling that is to control all those degrees of freedom, but another way of controlling that to have a 1 degree freedom controller that just says +1 goes to the right and -1 goes to the right and to the left, and that is enough. So conditioned on me knowing that this is a sine wave, I should be able to do this task. All right, so how do we do this? So basically using that insight, we are collecting expert demonstrations from a caregiver or an expert, which is basically state actions and beliefs. And from that, you're encoding that data into a latent action representation, so Z1 and Z2. And the idea is, again, conditioned on the context, which is the states and beliefs here, we are able to train a decoder that reconstructs the same actions. And when you're training this autoencoder to get these action representations, you need to ensure that the loss function captures things like reachability or controllability, temporal consistency, and things of those form. And at the end of the day, you're getting like a 2 degree freedom controller that just does the task. Let me show you how this works in practice. So here I'm comparing end effector control, where we have 6 degrees of freedom, and latent actions, where we have these 2 degrees of freedom. And again, latent actions is much smoother and easier to use. You can easily move between the shelves for this long horizon task of making an apple pie, which is kind of nice and faster and more intuitive for the user. And on the left, you can see that the user is just having a hard time getting outside of like these modes, these linear modes and angular modes. All right, so latent actions, they're intuitive and they help us basically have these low dimensional controllers. But the question that we've been thinking about since then is this enough for precise manipulation? And we have done some work along these lines of making this a little bit easier. But because I don't have that much time, I'm gonna quickly just leave you with one thought that I'm really excited about, and we're actively working on it, which is basically this idea of trying to improve teleoperation here using shared autonomy and enable people to use these robots to feed themselves. I think assistive feeding is an incredibly exciting problem and difficult. It's a difficult robotics problem because you're picking up like food items that are deformable and they change over time even. And then it's a difficult human robot interaction problem because a fork with a food is coming to your face and you need to make sure that it is safe and it is comfortable. And even if it is scraping the food inside of your mouth, it is doing it with the right forces in a way that is safe and so on. So we're collaborating with people at UW to better understand this problem. It's a difficult problem to also do during COVID times. So with that, I've been basically talking about this idea of learning intuitive controllers using latent representations. And that basically brings us to the fact that we can learn from humans. We can use these latent representations to make it easier to better coordinate. But the thing that I kind of skipped and I want to go back to and end the talk with is this idea of non-stationarity. I kind of like skipped that at the end, like for these two vignettes of learning reward functions and assistive teleoperation. But I do think that this is incredibly important, like the fact that people change and they're non-stationary. And we often tend to not worry about it as much because we are all about making an autonomous system, an assistive system, or an autonomous car that just does the task right? And we often don't really think about long-term interactions. The fact that when you put that system in a person's life, over time, that person is also learning, that person is also changing. And we should be able to capture that. This is a problem in assistive robotics. This is a problem in using these exoskeletons in rehab because the robot doesn't model the human. And one of the biggest problems there is over assistance, where it just does all the job because it doesn't capture the fact that the human is learning. This is a problem in driving. Like imagine that example I was talking about when the car cuts in front of you. That is going to work in that one particular step interaction. But that can make this car really angry, this black car, and it might come around and get ahead of you. And we should capture the fact that we are influencing people, and those influencing behaviors can affect people's policies, people's reward functions, and they're non-stationary. And I want to emphasize this is incredibly important because as we are putting in more systems, more autonomous systems, autonomous cars on the road, it's not in a single autonomous car and worrying about the perception and planning of that single autonomous car. It is really about that interaction of that autonomous car with a whole group of people and how that changes the full dynamics of driving and what sort of conventions do we get when we think about repeated interactions. So with that, I think we should think about all these challenges: non-stationarity, coordination, and influencing. And I think latent representations provide a perspective on achieving this idea of collaborations and interactions more effectively. And I think we should try to learn from humans and bring that in the learning loop. With that, I'd like to thank the group during COVID time, and then thank you guys, and I can take any questions.
Thank you very much, Dorsa, for that inspiring talk. There are, let's see, there's a couple of questions. Maybe I'll just moderate. We have about a minute, so maybe we can ask two questions. The first question is about features. So the first question asks, if you use features extracted from data using unsupervised learning, do you see value in combining them with Gaussian processes rather than deep learning?
That is interesting. Yeah. So the Gaussian process there was basically bringing down the space that we are doing active learning over. So if we have like a deep neural network, like there's still like big questions there of how are we going to combine ideas around active learning there and how we're going to be smarter about the data that we collect. I think that could be combined with Gaussian processes, and that could be a good way of going about learning reward functions and even like doing things like safe learning, which is more plausible, like more easier to do with Gaussian processes as opposed to deep neural networks.
Okay, maybe I'll fit one more question in before the deadline. The next question is, do you think that we can scale to learning from different humans with different preferences simultaneously?
Yeah, that's a very good question. That's something that we're actually looking at actively right now. So yeah, so if you have data from multiple humans, then you have like a population data, and that could be a mixture model. So the question there becomes, how can you learn from mixture model, like from settings where you have these mixture models, and how could you do active learning in that setting? Like how could you actively generate queries from and be able to differentiate between these different humans when you have, let's say, a mixture of Gaussians or a mixture of different types of reward functions. It is actually a difficult problem, both theoretically and also practically. It's also not clear if active learning particularly helps in that setting or not.
Mm-hmm. Thank you, Dorsa. We have a couple more questions, but I think we'll leave them to type some answers and we'll move on to the next session. And thank you very much for that great talk.